All right, well, welcome to Mathematics 30-2, Perms and Comms Lesson 3 for Shaughnessy's class. Standard disclaimer, please feel free to stop and pause and read it. Otherwise, we're going to kind of keep going and go on. And so, Perms and Comms Lesson 3. The last two classes, we spoke about the fundamental counting principle, and then we spoke about a basic introduction to permutations. What I want to do right now is more complex permutations. As you do things that are similar or a little bit more convoluted, it takes a few more things just to think about. So complex permutations, okay? There's lots of restrictions, or there's multiple copies of identical elements. Now it's this that's the biggest thing. The lots of restrictions just takes a little bit more thinking. But the multiple copies of identical elements. So you've got multiple copies of the 5 that are going to be distributed, or you've got multiple copies of the letter A, or you've got multiple identical chocolate bars, that sort of thing. In that particular case, even if you're not repeating them, there's sometimes you're going to end up having the same thing show up. And so you end up with situations where it doesn't really look any different. I mean, for example, imagine these are Scrabble tiles and I had A, B, C, A, those 4 Scrabble tiles. Now they're all identical. If they were Scrabble tiles, I can't see any difference. Now if I took them and swapped them around, okay, I'm busy trying to find a word. If I switch this A with this A, it doesn't look any different. And that's what we're talking about with like elements. You've got multiple copies of the same thing. Now permutations with like elements, okay, first off you're arranging all of the objects in a set, okay? So you're going to arrange all of them. You're not just going to pick and choose a couple of them. You're going to arrange all of them. But what you're going to have is you're going to have n pick n. Now, I know the formula is n pick r, but the reason I've got n pick n is because there's 5 objects, you're taking 5. They're going to be the same number every time. 7 objects, you're taking 7. 12 objects, you're taking 12. Could also be written, if you did the formula, as n factorial. However, it's the same thing. So these are identical, n pick n or n factorial. But what you're going to do is you're going to divide out the like elements. You're going to divide out the objects that are the same. So if you have little a of one element, you're going to divide by a factorial because you have a copies of an element. So you're going to be dividing by a factorial because you have a copies of some element. In this particular case it would be 2 factorial because I have 2 copies of the letter A. And you just keep going that. You're going to multiply or divide by b factorial. You're going to divide by that because you have b copies of another element. Okay, and so sometimes you have multiple things. I could have A, B, C, A, and then I could have D, D, D. So I have 2 copies of A and 3 copies of D. So I'm going to divide by 2 factorial for the A's and 3 factorial for the D's. Okay, and so on and so forth because there's 3 D's. Same thing if you did it in factorial to start. You're just going to divide by a factorial, b factorial, and if there are more, you do more. If there's 3, then it would be a factorial, b factorial, c factorial. You just continue. But at any rate, you're doing that. Now, when you go to type that into the calculator, though, the one thing I want you to be conscious of is when you're doing this. For example, I'm just going to make one up. Okay, I'm making one up. Don't wonder where this comes from. 10 factorial divided by, I have to put that bracket because when I'm dividing by a 3 factorial times 2 factorial. I have to put that bracket. Without that bracket, oops, my apologies here, busy having trouble pushing buttons. without that bracket there, okay, I'm only going to divide by the 3 factorial, and then once that's done I'm going to multiply whatever is resulting by the 2 factorial, and the 2 factorial doesn't get divided out, it ends up getting multiplied in. So you have to remember that bracket when you go to type it in. Okay? But going through, that's how you deal with elements that are identical. Now in some cases you've got objects that are just, have multiple restrictions, that sort of thing. So let's do some examples. How many different numbers greater than 200,000 can be formed using the digits 1, 3, 5, 7, 8, and 9 if there are no restrictions? So 1, 2, 3, 4, 5, 6. There are 6 digits that I can choose. How many different numbers greater than 200,000? So since I'm allowed, it doesn't say there's no restriction, so I'm allowed to repeat elements. Okay, I need greater than 200,000. There are 6 digits, 6 spots. The 3, the 5, the 7, the 8, and the 9 can go in the front. The 1 can't, because if the 1 goes in front, it's not greater than 200,000. So there are 5 options there. But if I can repeat, I've got that, and then the second digit, 6, and then the third digit, 6 choices, fourth digit, fifth digit, and finally the 6th digit. And so I end up with that. If there are no restrictions, I've got this as my situation. So it's 5 times 6 repeatedly, and ultimately my handy dandy calculator says that that is 38,800. 880, sorry. Okay, so you've got that. If the number must be even, then I get a few different things. Okay, if the number must be even, I could have an 8 at the end, or I could have an 8 in the middle. Now, if I have an 8 at the end, okay, that's going to make it even. So the 8 at the end, there's 1. That's the only way I'm going to make it even, using a 1, 3, 5, 7, 8, and 9. Okay, the number must be even. The other 5 digits I have to fill in. Now, the 8 is at the end, so the 8 is now gone. Okay, I'm allowed to repeat it. It doesn't say I can't repeat. So now I go back over here. Well, the only one I can't use here is the 5. So I put the 5 there. And then after that I've got 6 choices, 6 choices, 6 choices, and 6 choices all the way through. Okay, so I'm done. If I don't have an 8 at the end, okay, then I start to wonder, well, what's going to happen? So if I don't have an 8 at the end, but I still need it to be even, I still have the 6 blanks. If there's no 8 at the end, how many choices can I put here to make it even? 0. Now, after that, I've got 0 times anything. There's no way that I can have an 8 in the middle and still have this. Okay, so the 0 times this times this times this times this times this, doesn't matter what these blanks are, it doesn't matter. By the 0 times everything, the whole thing is 0. So all I've got is this: 5 times 6 times 6 times 6 times 6 times 1. That's the only way to do it. But I'm looking at the multiple cases, because you never know if something's going to cancel out. So in this case here, I've got 5 times 6 times 6 times 6 times 6 times 1, and that is 6,480. So there are 6,480 numbers greater than 200,000 from that set of digits that must be even. Okay, continuing on with that, I don't have any identical elements there, but I do a little bit later on. Okay, when it comes to these ones, how many distinguishable arrangements are possible of all of the letters of these words? Well, first off, I look at Edmonton. Now Edmonton has 1, 2, 3, 4, 5, 6, 7, 8. 8 letters. Okay, so I'm arranging the 8 letters, so I have 8 pick 8. However, I'm paying attention by the fact that there are at least 2 O's. So since there are 2 O's and 2 N's, I've got to divide out those like elements. So 2 factorial for the O's, 2 factorial for the N's. And what I get is this: 8 pick 8 divided by 2 factorial, 2 factorial. So I figure that out, and I'm just going to my handy dandy calculator. And this answer is, if I've done it right, 10,080. So there are 10,080 distinguishable or distinct. Basically that means you can tell the difference between them. And now if they're all capital letters with those N's or those O's, I can move them around and you can't tell the difference. So it's not distinguishable. Whereas these ones now, I've divided out those repetitions so the 10,080 are distinguishable arrangements. When I look at Calgary, there are 7 letters, so I can do 7 pick 7, or I'm going to this time do 7 factorial. Now looking at that, I've got 1, 2 A's, and that's it. So I'm going to divide by 2 factorial there. So I've got 7 factorial divided by 2 factorial, or 7 pick 7 divided by 2 factorial, however you want. And when all is said and done, I'm just doing the math, that is 2,520. So there are 2,520 distinguishable arrangements of the word, or the letters of the word Calgary. If I look at Lethbridge, it's 4, 6, 7, 8, 9, 10. It's 10 pick 10, or 10 factorial. I'm going to write 10 pick 10 this time. And looking at this, there's 1, 2 E's. So 2 factorial for the E's. And I'm just looking at this again and I don't see anything else. So I've got that. So 10 pick 10 divided by 2 factorial, and I just go figure that out. Sorry, doing the math here, pushing the wrong button. And so what I get here is I get 1,814,400 distinguishable arrangements of the letters of the word Lethbridge. Now in each case I had 2. So 2 N's, 2 O's, 2 A's, 2 E's. Okay? If I had had 3 N's, if it was Nedmonton, which there's an N in front, if there was Nedmonton, then I would divide by 3 factorial in one of these situations. Okay? Continuing on, a 13 question test has 4 A answers, 3 B answers, 4 C's, and 2 D's. How many distinguishable keys? Now this is assuming I can rearrange it and however I want. Well, that's 13 questions, so it's 13 pick 13 or 13 factorial. There are 4 identical A's, so 4 factorial for the A's. 3 identical B's, so there's 3 factorial for the B's. 4 identical A's, so 4 factorial for the C's. And 2 identical D's, so there's 2 factorial there. And all I've got to do is figure this out. So I have 13 factorial divided by 4 factorial times 3 factorial times 4 factorial times 2 factorial. And I work this out, and if I've done my math correctly, this is 900,900. So there are 900,900 possible keys for this particular situation. So you have that option there. Okay, so if you have the same key or the same particular example as somebody, it's pretty rare. Okay, and that's 13 questions, not 15 or 28 or whatever else there might be. Now, in these particular situations here, these aren't drawn. The reason they're not drawn is because I don't have them yet. But the number of paths from A to B. Now, if I look at this first pathway here, and I'm just going to draw it, okay, I'm going to draw a square, or a rectangle, sorry. I'm going to put an A in one corner, and I'm just randomly choosing, doesn't matter, and a B in another corner. And I'm going to put 3 lines going down and 1 line going across. And I want the paths from A to B. Now this is an application of the permutations with repetitions. What I have to think about is what's going on. I have 1, 2, 3, 4, 5, 6 blocks. If I'm always getting closer to B, I have to go 6. It doesn't matter whether I go around the edge, 1, 2, 3, 4, 5, 6. Doesn't matter how I do it. 1, 2, 3, 4, 5, 6. It doesn't matter how I do it, but I can count this. And honestly, that's as scientific as it gets. Count that 6 factorial. So there's 6 blocks, so I've got to go 6 pick 6 or 6 factorial. 4 of them are across left to right. So I'm going to divide by 4 factorial. And 2 of them, counting them right there, 2 are up down. So there are 2 identical up-downs. And that's the situation here. 6 factorial divided by 4 factorial, 2 factorial. And that's going to be 15. Okay, so you've got that. Okay, now pathways can get a little bit more complicated, but it's still the same idea. This one here, looking at this path, I'm going to go from A to B. and I'm not putting b at that corner. May have accidentally made you think that. I'm drawing another little path, and that one's going to be 2 by 2 down there. Here I'm doing 1, 2, 3 lines in between, and 1, 2 lines across. Now what happens is I have to go through this pathway and this pathway. So as soon as I say and, we've talked about it before, it's a multiplication. So I've got two things to consider. In the first pathway I have to go 1, 2, 3, 4, 5, 6, 7 blocks. So I'm going to have 7 pick 7 or 7 factorial. I'm going to write 7 pick 7 this time, divided by 4 across, 4 factorial, 3 up and down, 3 factorial. Once that's done, okay, and means multiply, I've got to go through this pathway. Now in this pathway, using a different color, is 1, 2, 3, 4. There are 4 blocks that I have to go. I don't think that shows up very well, but 1, 2, 3, 4. So it's 4 factorial, or 4 pick 4. I'm going to write 4 factorial this time. 2 are across the sideways, so across the top, and 2 are down, so 2 factorial. And what I'm going to do is I'm going to take these and I'm going to multiply them. So it's going to be 7 pick 7 or 7 factorial divided by 4 factorial, 3 factorial, so it's going to be so that's going to be 35, I think, times this one here is going to be 6. So I have 35 times 6, which ends up being 210. So there are 210 distinguishable paths from A, and I forgot the B in this corner, to B. Okay, so you've got that. Continuing on, we've talked about these sorts of things. Parent wishes to distribute 6 ice cream cones to his 6 children. He has 3 chocolate, 1 vanilla, and 2 identical mixed. If there are no restrictions, well, 6 pick 6, or 6 factorial. That's just like we've been doing. So that is, I believe, 720. If the oldest must have vanilla, well, I've got the oldest has to have, he has 1 choice for vanilla. And then I've got 5 others. For those 5 others, I've got to do 5 pick 5, or 5 factorial. That ends up being 120. Okay, oldest and 5 others. Here, if the oldest must have vanilla, okay, so I'm like, okay, I can do this. The oldest must have vanilla. Then I've got 4 others. Then I've got the youngest must have mixed. Well, the youngest has 2 choices for mixed cone. There are 2 options. Okay, for the remaining, it's got to be 4 pick 4. Now, what have I made a mistake? I have absolutely made a mistake at this point. I apologize. Because if I've got 3 identical chocolate, 1 vanilla, and 2 identical mixed, I'm going to divide by the 3 factorial, the 1 factorial, which I'm not going to write, and 2 factorial for the mixed cones. And so this is going to be divided by 3 factorial, 2 factorial, which ends up being 12, just so you know. So 720 divided by 12 is 60. There are 60 possible distributions, distinguishable distributions of these. If the oldest must have vanilla, well, I've still got the same thing, where I divide by the 3 factorial for the 3 chocolate cones and the 2 factorial for the mixed cones, and so I'm going to divide that by 12, and that's going to be 10. There are 10 possible distributions if I have the oldest having vanilla. In this particular case, the oldest must have vanilla, so dividing by 3 factorial, 2 factorial, and what I end up with is 4. Okay, I just did the math. If I crunch the number, oldest must have vanilla and the youngest must have mixed, there are 4 possible distributions. Okay, so that's the situation that I've got there. Okay, and so I apologize for forgetting to divide out the repetitions. My whole lesson is on that and I forgot it, so I apologize. Continuing on, how many distinguishable arrangements of the letters of the word carrier are possible if there are no restrictions? If there are no restrictions, there are 7 letters, so it's 7 pick 7, or 7 factorial. And what else I've got? I've got 3 R's, so I'm going to divide by 3 factorial. And so 7 factorial divided by 3 factorial is 840. So I've divided out the repetitions. Sorry, I wasn't watching that in the last one. But nonetheless, there we go. I've divided out the repetitions. Now continuing with this context, okay, letters of the word carrier, so I'm just going to write that up again here, C-A-R-R-I-E-R, okay, just for reference. If the first letter has to be an R, well, in this case I've got 3 choices for that R, and then I've got 6 other letters to choose from, and I've got to pick 6 of them. Now I'm still dividing out the repetition, so I'm still dividing the 3 factorial out. And what I'm going to get is, I believe, if I've done my math right, 360. So there are 360 arrangements if the first letter is an R. Now I can just keep going with this, keeping this idea going. First 2 letters are R. Well, in that case I've got the first letter, 3 choices, the second letter, 2 choices, and then 5 others to go. But I'm still dividing by the 3 factorial. And if I work this out, 3 times 2 times 5 factorial divided by 3 factorial, I'm going to get 120. There are 120 arrangements for that. Continuing going, the first 3 letters are R, R, R. Well, first letter, 3 choices. Second letter, 2 choices. Third letter, 1 choice. And then there are 4 letters left to go. And I've got to divide by the repetitions, the 3R for the 3 factorial for the 3 R's. And when I work this out, what I'm going to get is 24. I'm just doing the math. So all of a sudden now you can see how I'm dealing with the repetitions. I'm still arranging all of the options, all of the situations, but I've got some things to consider. Going with this one, first letter is R and the second letter is not R. Well, there are 3 choices for that first letter. And then, out of the rest, if the next letter is not R, I've got 1, 2, 3, 4 choices for that one. So that's going to be 4. Then I've got the remaining 4 letters, or the remaining 5 letters, sorry. Yep, 5 letters. Sorry, I had to count. So 5 pick 5. In that case, though, I still have to divide by the 3 factorial for the 3 identical R's. And what I end up with is 240. So I've got 240 arrangements of that. If the first 2 letters are not RR, that's my next one. Well, in this particular case, I have the total. I'm thinking, well, how do I arrange this? The total minus the ones that are RR. No pun intended. The reason I'm not attacking it directly is because if the first 2 letters are not RR, I get into a kind of a convoluted situation. The first letter's R and the second letter's not R, or the first letter's not R and the second letter's R, or the first letter's not R and the second letter's not R, and I have a bunch of cases to consider. And in each case I'd have to say this, or it could be this, or it could be this, and if I miss a case, I miss the whole thing. This is the quickest way to do it. Now looking back at my answer for A, way back at the beginning, there are 840 ways that this could be done, or 840 arrangements in total. The ones that were RR are back up here in C. The ones that are RR, start with the first 2 letters R, are to 120. So I'm going to take the total arrangements minus the 120 that I don't want. And when I work this out, I'm going to get 720. And that's going to be my answer for that. Continuing on with just some other ideas. There are 3 couples, and I'm assuming that there's 1 man and 1 woman in each couple. I know it's not that simple, and I know it's not always that way. However, just for the purposes of this question, it makes it easy. Okay, so 3 men, 3 women arranged in a single line for a photo. How many distinguishable photos are possible if there are no restrictions? Now, if there are no restrictions, I've got 6 blanks. And I've got 6 choices for the first person, 5 choices for the second, 4, 3, 2, and 1. So I basically end up with 6 factorial, or 6 pick 6. Okay, could write it any of those ways, which is 720. So I'm like, okay, that's done. I've got 720. Now if I must alternate 1 man and then 1 woman and continue this pattern. So I've got Now, 6 blanks, 1 man. There are 3 choices of men. There are 3 men. Then 1 woman. Doesn't have to be the matching woman or the partner or the couple or the spouse or however you want to call it. So there are still, I know it has to be a woman, there are 3 choices for women. After that, now I've got one of the men placed, so there are 2 choices of man left, and there are 2 choices of woman. Then there's 1 choice of man, then there's 1 choice of woman. So I've got this. Okay, so 3 times 3 is 9, 18, 36. So there are 36 ways, or 36 arrangements that can be done. If the couples must stand together with the man on the left. So once again, 6 blanks. There are 3 choices for that first man. But once that's done, it has to be the woman that matches up. So there's 1 choice there. 1 choice there. Then I get another man. There's 2, but there's 1 woman that matches up with that person. And then 1 choice there. And there's 1 woman that matches up with them. And in this case, it's 3 times 1 times 2 times 1 times 1 times 1, which is 6. There are 6 arrangements if the men have to be on the left. Okay, continuing on with this sort of idea, if the couples must stand together. Well, if the couples must stand together, but it doesn't have to be a man, this one here gets a little bit more complicated because it doesn't have to be a man to start. So the couples must stand together. There are 6 choices for that first person. I can put any one of the 6 there. But whichever one I put there, there's only 1 choice for the person next to them. Then continuing on, I've placed 2 people, I've got 4 left. So there are 4 choices for this next person. But once again, whoever I put there, there's 1 choice for the person next to them. Whether this is a man or a woman, or whether this is a man or a woman, the opposite or the partner or the other half of the couple has to be next to them. So I have that. When I go to this last one, I've got 2 choices there. And then I've got 1 left. So man or woman, partner. Man or woman, partner. Man or woman, partner. And then when I go with that, I end up with 48. There are 48 arrangements that have the couples together. If the couples cannot be together, this is another one where I'm like, well, okay, so I'd have the couple and then somebody that's not, so it's 6 times and then there's 4, and I end up with confusion with that. The easiest way to do these ones is the total minus the ones where they are together. So the total, I'm looking back at A, the total was 720. The ones where the couples are together is 48. Okay, so I have 720 minus 48. And if I'm correct, that's 672. Just give me a sec. Minus 48 is 672. I didn't trust myself. Did you notice I had to use my calculator? But there we go. That is kind of the end of this introduction to the complex permutations and the permutations with like elements. I hope that makes sense. If you have any questions, please contact a friend, contact myself. There are further examples in class. Please attend class if you can next period. Thank you and have a great day.